And then we have Nabel Rehemtulla. Where is Nabel? Oh, there he is. From Northwestern, telling us about real-time workflows for transient discovery. No. Change the title.
Yeah, shuffle the title around. Yeah. Thank you. Hello, everyone. My name is Nabel Rehemtulla. I'm a fifth-year graduate student at Northwestern working with Adam Miller. And I'm very grateful to be speaking to you today, particularly at this fantastic venue that the organizers put together for us. So thank you to them. Now, this week, we've had a lot of fantastic talks on all of the hard work that goes into infrastructure, from the surveys, the alert generation, alert brokering, follow-up, the whole spectrum of it. And what I want to talk to you about is a little bit of the science that is enabled by these state-of-the-art infrastructure. And if you don't already feel like this, I hope by the end of the talk, you feel like all the hard work going into the infrastructure is worth it. Okay, so let's start with a little bit of science background. So I'm interested here in infant supernovae. So these are supernovae caught within the first few days after first light. And it turns out that getting spectra of these infant supernovae can reveal otherwise unobservable information about the progenitor stars. Okay, so in this case, I have a spectral series of a type 2 supernova, and it's exhibiting this phenomenon called flash ionization. So this involves these narrow, short-lived emission features, which are telling us that there is this dense circumstellar material immediately outside the surface of the red supergiant progenitor. Okay? Now, to understand how that material got there, we infer that the red supergiant must have underwent this enhanced mass loss phase, throwing off mass 1,000 times or more quicker than a quiescent red supergiant. And the way we learn about this a little more is to learn about to study the properties of these flash features, these narrow emission features that I'm highlighting here. So the strength, the duration, and the species we see in the emission tell us about what the red supergiant is doing before the explosion. Okay, so the early data is very important, but there's this critical misalignment where our workflows for getting these early spectra are not very conducive to actually getting them as early as we need. So here's a metric I'm calling spectroscopic follow-up latency. This is the amount of time that passes between the first detections of a supernova and our first spectrum of it. And I've limited this to just the nearby supernovae discovered in ZTF, so the ones that are the most critical to study and capture early. And you can see here that this distribution, the median here is actually more than 1 day, more than 24 hours of latency that we are imposing on the follow-up, namely by requiring manual human vetting to identify candidates and trigger follow-up. Right, and this is important because the phenomena we want to study are evolving on shorter timescales than our actual latency. Okay, so we're missing the earliest, juiciest physics here. It's much the same case in the UV. Here I have a collection of UV model light curves where the different models are using different mass loss rates of the progenitor star. So again, directly probing the physics that we want to learn. Here, the absolute magnitude is not as constraining as it may seem, but what really matters is the rise timescale. So again, early time data is the most important. And once again, the latency in the workflows is critical here. The horizontal shift between the red and the blue CDFs are what we're going to look at. And this is about 1.5 days. So again, we're actually slower in the UV than we are in the optical. So my title may have given away that I'm interested in automating the supernova identification and the follow-up. Okay, so you probably understand by this point in the week that this is a filtering problem. Because we're looking only at the nearby supernovae, approximately 1 per few weeks. An average night of ZTF gives you hundreds of thousands of alerts, but exactly 0 of those on most nights are the real new nearby supernova we want to trigger our rapid follow-up on. And the 1 night a month-ish, when there is that supernova there, we need to find it and act decisively with minimal information, right? We have maybe a couple of photometry points, some cutouts, some catalog cross matches, and we need to go and trigger our biggest and best follow-up facilities to get that valuable early time optical spectra and UV light curves. And of course, when we're triggering follow-up, there's minimal tolerance for error. Now, what I'm showing you on the right here is actually not a nearby supernova. This is an illustration of why this is so challenging. This is a terribly convincing false positive. It may be hard to see in the projector screen, but there's actually a satellite streak dancing through the image here and another one through here. This actually happened on the night of a Starlink launch. So we think this is a Starlink satellite. Again, a terribly convincing false positive that we need to be rejecting with minimal information and following with decisive actions. Okay, so my solution for this is an artificial intelligence model I've created called BTS-Bot. So this is multimodal using images and metadata together to simply just do supernova, not supernova in the ZTF alert stream. Okay, now I could give an hour-long talk on all of the ML and data engineering that went into creating and training BTS-Bot, but I think for this venue, I want to talk about something a little bit different. What I did in a recent study, actually, that was accepted a couple of weeks back, is I took a step back and I looked at what's the playbook that we time domain astronomers use for making models like BTS-Bot. So I looked over more than a dozen studies, and almost all of them had exactly the same methods. They'll design a custom architecture CNN, so they'll take one convolutional layer with these parameters, followed by another convolutional layer with these parameters, and so on. And they'll take that architecture and train it from scratch. Okay, so this works. Admittedly, this is exactly what I did for the original BTS-Bot study, and it's what has served us reasonably well in the past. But this does not scale. When we're in this era like we are today, when we have many surveys operating simultaneously, each needing their own computer vision models for real bogus or for whatever else, we need to have a more efficient, more modern philosophy for designing these models. And that's what I did in this recent study. I started adopting practices that are used, the standard and best practices used in the computer vision literature, rather than what silly astronomers do. And so the first kind of pillar of this is pre-training the network. This is a relatively simple thing. Just pre-training on Galaxy Zoo data, we showed that it confers benefits in efficiency with the data, critically the limited labeled data that we don't often have much of. Multimodality, astronomers are quite good at this. We heard about a number of talks involving this. But lastly, and perhaps most importantly, is adopting off-the-shelf architectures, right? So instead of doing this, I want this layer followed by this layer, we can go to a study from a real computer vision scientist and just use their work. We can just take their model, and you can imagine it is much better optimized than what what we astronomers can do when it is their main job is to make beautiful, optimized, efficient networks. And so we showed that simply taking a network off of the shelf can substantially reduce your computational cost and save a lot of researchers' time for astronomers. So we're really pushing that we can update the practices for these vision models as new surveys come online. Now, I kind of alluded to this earlier. There have been a number of studies that have done supernova identification with machine learning. But what really makes this work stand apart is the seamless integration with the ZTF discovery and follow-up workflow. And as of today, BTS-Bot, this AI model I've created, can fully autonomously trigger facilities across the globe and beyond, including the SED machine here in California, the SOAR 4 meter in Chile, the MMT 6.5 meter in Arizona, the Gemini 8 meters, and most excitingly, the SWIFT space telescope in very low Earth orbit. And it must be said that this work is only possible with very special contributions from computational scientists here at Caltech and research software engineer at Minnesota. So I promised science. Let's get into some of the science results we've had with this. So the kind of story for this started with the supernova 2024 JLF in May of 2024, where ZTF detected the supernova about 0.7 days, so 16, 17 hours after first light. In the real-time stream, BTS-Bot automatically identified it, triggered a rapid response request to the SED machine, which observed just 20, 25 minutes later. So that gives us this spectrum starting 0.7 days after first light. And here we are seeing, in the spectrum in the following ones, this beautiful flash ionization phase. It's much weaker here than in the example I showed earlier, but these are the narrow features that are telling us about the CSM and the mass loss properties of the progenitor. Now, what's really turned out beautifully here is that the flash features disappeared here after just 48 hours. So in this 1.8 day spectrum we obtained, you can no longer see these narrow emission features. So if you kind of think about the typical latency that I said that we usually have, about 1 day, if you add that to our discovery epoch, you're at a point where you're no longer seeing the flash. And so if we had the typical latencies that we didn't have BTS-Bot in this case, we would have probably entirely missed the flash and not been able to learn nearly as much about the supernova or the star that created it. So I started with this figure a while back. Again, the latency in our human-based workflows, if you will. And if we overlay what we've demonstrated with BTS-Bot for the past couple of years, you can see we've seen a more than order of magnitude decrease in latency from the detection, the initial detection to the first spectrum, from more than 1 day down to about 1 hour. The story gets more exciting in 2025 with the supernova 25 QTT, where once again, we have a BTS spot SCDM spectrum starting quite early, and we see these really nice and stronger flash ionization features. In this case, what happened was actually this really nice spectrum here was not obtained by us, but it was obtained by an independent group over in Hawaii, because they told us they saw the report that we put out publicly immediately after discovering this. And so all of our reports are instantaneously and automatically reported to the public, and this is clearly helping others beyond our group help get really exciting data on these phenomena as well. But the really highlight here so far is the fully autonomous communication with the Swift Space Telescope. So following the automatic discovery, BTS bot triggered Swift to get near instantaneous follow-up, and just 6 minutes later, Swift is on target and collecting UV photons from the supernova. Now, I want to emphasize that this is only possible without humans in the loop. Whenever we have humans requiring approval of triggers or discovering the transients in the streams, there is inevitably a much larger amount of latency here. Now, I also want to say that this AI Command Space Telescope is more than a fancy headline. It really is what we need in this infant supernova space. The UV light curves, especially the rise, which we caught here, is very tightly correlated with the CSM and mass loss properties of the progenitors. This is information that we usually cannot get because we're just a little too slow. And so accelerating the workflows with this allowed us to capture this data and get a much better handle on modeling it and learning about the astrophysics of the progenitor. Okay, to summarize, with BTS Bot, we're demonstrating the power of AI-driven human out-of-the-loop workflows. We're doing this with ultra-rapid ground and space-based follow-up, demonstrating a more than order of magnitude decrease in the spectroscopic follow-up latency. And I have a couple discussion points here we can get into if people are interested, but I'll stop there. Thank you so much.
Very nice talk, Navi. I was just curious, was this bot active when 23IXF went off? Because I think ZTF got it before it was reported, right?
Yeah, so two things. It was not active in this very rapid response mode. But the problem with that very, very early IXF detection is that there was only one of them. And up until now, through now, we require 2 detections in order to reject moving objects. And so we've been working with ZTF to kind of steer the cadencing of the partnership and Caltech time to get more frequent coverage of nearby galaxies to try and catch the once in a decade type events more quickly.
Thank you.
I mean, if it's a truly once in a decade thing, couldn't ZTF stop what it's doing and just go back and look? If you have a true high ML score thing in M101, and you could find, the next of it, why go through all this when you could just go back and look if you have a high ML score?
Well, you didn't know with confidence that it was real at the time.
I understand. But I guess I'm making a suggestion that maybe for very nearby galaxies, if you have something that's 80% confident, maybe you should just go back and look.
Yeah.
Is it doing anything? ZTF is great, but this could be the once a decade thing, right? Yeah. But could there be an automated TOO for things in M101, M51, et cetera? Yeah.
We can do it with ZTF, or we could even do it with SCDM as well, or whatever. The APIs here are all agnostic, so BTS Bot can trigger whatever it wants.
Just a suggestion, yeah.
Yeah, so actually, I can say I've played around a little bit with removing this moving object requirement, and the alert stream is really, really messy when you don't do that.
Even for just
I think the nearest ones are actually harder, right? You have a larger angular size. You just have more sky where you can get junk showing up, and you have much brighter backgrounds where subtractions are difficult. But yeah, there absolutely is work to be done and opportunity.
Hey, Nabil, this is great. And this is not really feasible with facilities like DECCAM or PanSTARRS because the data processing itself takes so much time that, the images don't even show up on disk to do this analysis. Rubin does the processing for images within 60 seconds, but the Rubin cadence is such that it's very hard to get two detections which you need for streak removal or raster removal or moving objects. If you had to modify the Rubin cadence in such a way to facilitate this science, what's the easiest way to do it? Is it, take two pairs of images at each location and two different filters right back to back, or is it a wider space triplet? And I'm also saying this fully aware that Mansi's on the science advisory committee for Rubin. So
Yeah, we've asked this question in ZTF. And like I said, we've been doing a little bit to steer the cadencing of the partnership and Caltech survey. So actually Eugene has done some really nice work estimating like the supernova rate per ZTF field. And we're steering to do, I think it's at least 2 visits now per night for a lot of those fields just to maximize, nearby supernova discovery.
Okay, we have a very pressing question, but we should also start moving towards the. So let's first thank Nabil again.